Hello students, today's class will study about working of Xenadiode as a voltage regulator. So please say the question. With the help of a circuit diagram, with the help of a circuit diagram, explain the use of Xenadiode as a voltage regulator. With the help of a circuit diagram, explain the use of Xenadiode as a voltage regulator. Okay. Now what is voltage regulator? If any fluctuations are the input side, those are not reflected on the output. Output voltage remains constant. Now this regulator applies only for the DC, not for the AC. So which component is used here for regulation? A Zener diode is used. So we'll draw the circuit diagram. Okay. So it's a plus and here is minus. And we'll take one Zener diode. Which is reverse bias, and we'll take one load resistor. We'll take one load resistor. Here you are going to give unregulated DC voltage, and here comes a regulated DC output voltage, and here one resistor is used to control the flow of current. This resistor is must, and this Zener operated under reverse bias. Now this diode and normal PN junction diode, there is no difference in the forward bias. The difference comes only in the reverse bias. Okay, so just will complete the circuit diagram. This is a resistor R L. Okay, here comes the output. So this is unregulated DC voltage. Unregulated DC voltage. Okay, and this is RS here, Zener RL, and here becomes regulated DC output. Regulated DC output, here become plus and here is minus. This is plus because the Zener diode becomes a reverse bias here. This is a Zener diode and this is a symbol of the Zener diode. And if you draw the circuit diagram, circuit diagram is over. Now one waveform is there, that also important. We should draw that one. So the Zener diode operated in the reverse bias. So graph comes in the third quadrant. Okay. So it's a voltage along the x-axis and current along the y-axis in microampere. So what type of graph we are going to get? We'll complete the graph here. So graph comes something like this. Okay. A straight line here. This is a breakdown voltage. We call it as IZ. Sorry, VZ. So I'll extend this line somewhere here. This I call it as IZ minimum. And somewhere here I call it as IZ maximum. This is the regulating region. Regulating region. This is the regulating region. So we'll write the working of this one. Working. So it's a circuit diagram is over. Just we'll write the working. When input voltage increases, when the input voltage when the input voltage increases, when the input voltage increases, what happens? The current through RS and that through the Zener diode will increase. When the input voltage increases, current through the RS and that through the Zener diode will increase. This increase the voltage drop across RS, but the voltage across the Zener diode remains same. This is because in the breakdown region, the Zener voltage remains constant. Remains constant. Remains constant even though the Zener current varies. When the input voltage increases, the current through RS and through the Zener diode increases. When this unregulated DC voltage increases, current through this RS and Zener diode increases. So what happens? Voltage across this RS increases, but voltage across Zener diode remains constant. This is because in the breakdown region, Zener voltage remains constant even though Zener current varies. Now we'll write the reverse. Similarly, if if the input voltage decreases, the current through RS and Zener diode will decrease. Zener will decrease, but Zener voltage Vz will remain constant. The Zener diode thus the Zener diode acts as a voltage regulator. The Zener diode acts as a voltage regulator. If the input voltage decreases, current through RS and Zener diode will decrease. but Zener voltage Vz will remain constant. Thus, the Zener acts as a voltage regulator. So here Rs and one Zener is there, which are Zener and this Rs are connected in series and connected reverse bias. As the graph here, in the breakdown region, voltage across Zener remains constant, that is Vz written here. So current Iz minimum and here is Iz maximum. That is the regulating region. So input will increase, what happens? Current through Rs and Zener increases, but voltage across Rs increases, whereas Zener remains constant, because in the breakdown region, Zener voltage remains constant even though Zener current varies. If the input voltage increases, sorry, if the input voltage decreases, what happens? Current through Rs and Zener will decrease, but Zener voltage Vz will remain constant. The Zener acts as a voltage regulator. The Zener acts as a voltage regulator. Okay. So this much about the Zener as a voltage regulator. I will discuss some other things about gates. This was one important question is possible. Symbol of the gates truth table is a very one 2 mark question or multiple choice or fill in the blank question is possible here. So quickly discuss about the gates here. So next question we'll discuss about the gates. There are 3 basic gates and 2 universal gates. All the gates we'll discuss it again. First we'll start with the OR gate. So I'm not going to write the question here. First symbol will draw. Symbol of the OR gate. This is a symbol of the OR gate. Now this gate has minimum 2 inputs. It can have any number of inputs, but more than one. More than one, it can have any number of inputs. This is a symbol of the OR gate. So this is A and here is B. So Y equal how much here? A or B. Okay. Now what is the truth table of this one? This is a symbol. Now we'll write the truth table of OR gate. So there are 2 inputs are possible here. Inputs A and B, and there is an output. There is only one output, but there are 2 inputs. This is the truth table. Okay. So inputs and here is the output. So input A and B, output Y equal to A plus B. So 0, 0, 0, 1, 1, 0 and 1, 1. These are the possible inputs. When inputs are 0, 0, output is almost 0. Input is 0 and 1, output is 1. 1 and 0, output is 1. 1 and 1, output is 1. The gate whose output is 1, when any one of the input is I. When any one of the input is I. This is called as OR gate. It's similar to addition type, but we cannot call this addition. This is not actually addition. The gate whose output is high when any one of the input is high. This is called OR gate. This is the truth table here, and this is a symbol of the OR gate, and this is called Boolean expression. Okay, so I hope this is clear. So I'll go to next gate now. Next gate is AND gate. AND gate. AND gate. Same D is a, you can write here. This input is A, this input is B, and here is the output Y. Y is equal to A dot B. Okay. So we draw the truth table now. inputs and here is the output. So what are the inputs here now? A and B. Here is A and here is B. Output is Y equal to A dot B, which is similar to multiplication type. Inputs 0 and 0, 0 and 1, 1 and 0 and 1 and 1. The four combinations are possible because it's a two input AND gate. 0 and 0, so output is how much here? 0. 0 and 1, that also 0. 1 and 0, so 0. 1 and 1 becomes 1. The gate whose output is high when all the inputs are high. The gate whose output is high when all the inputs are high. This is called as AND gate. This is a truth table and here is the symbol of the AND gate. So next one is which gate here? This AND is over. Next gate is NOT gate. NOT gate. NOT gate. So what is the symbol of the NOT gate? Like this. This is a symbol of the NOT gate. Input is A. So output Y equal to A bar. Now what is the truth table of this one here? There is only one input for this gate and there is only one output. So here input A, output Y equal what you can write? A bar. So input is 0 and 1. So output becomes how much here? When input is 0, output become it's a reverse, that is 1. When 1 is the input, output become how much here? 0. This is also called as inverter. This is also called as inverter. So it's a NOT gate. A and here becomes what? A bar. Okay, so NOT gate is over here. So I hope this much clear. All the three basic gates we discussed. Next we'll discuss about universal gates. There are two universal gates are the NAND gate and NOR gate. So first I'll discuss with the NOR gate. NOR gate is a combination of OR and NOT. This is the OR and put one NOT symbol, this one. This is a symbol of the NOR gate. Truth table is, we have to go into this one, A plus B bar. This plus means OR here. So we'll draw the truth table of this one now. NOR gate truth table. Inputs and here is the output. Inputs A and B. So Y becomes what here? A plus B bar. So 0, 0, 0, 1, 1, 0, 1, 1. So 0 and 0 output is what? 0. It's a bar. So it's OR, right? So becomes 1. Here 0 and 1. Output of the OR is 1. So but complement here becomes 0. Bar is there. So 1 and 0, 1. But its bar becomes 0. 1 and 1, 1 bar becomes 0. So this is the truth table of the NOR gate. It is a combination of OR and the NOT. This is called NOR gate. By using this gate, we can design any other gates. Therefore, this gate is also known as universal gate. NOR gate is also known as universal gate. Okay, we'll discuss the next one now. Last gate. Next universal gate is NAND gate. Next gate we'll discuss, that is NAND gate. NAND gate. So what is the symbol of the NAND gate? This is A and here is B. So here become much y equal to a dot b bar. So inputs here and here is the output. So input here a and here is b. So it becomes what here a dot b bar. So 0 0 0 1 1 0 1 1. These are inputs. So what the output is possible? 0 0 output of the AND gate is 0, but its bar is just become 1. 0 1 output of the AND gate is 0, but its complement becomes 1. 1 0 output of the AND gate is 0, but its complement is 1. 1 and 1 output of the AND gate is 1, but its complement is 0. That means output of the AND gate you give it to NOT gate, so answer becomes its reverse. So in this place becomes 1 and here becomes 0. So what is one then? The gate whose output is low when all the inputs are high. The gate whose output is low when all the inputs are high. I'm sorry, low. Output is low when all the inputs are high. Or the gate whose output is high when any one of the input is low. That is a NAND gate. So NAND gate and NOR gates are known as universal gate. By using these two gates, we can design any other gates. Therefore, we call this gate as universal gates. Okay. So next there comes already discussed about AND gate, OR gate and NOT gate already we discussed. So I hope these concepts are clear here. And there one more question is in this chapter, classification of solids based on energy band. So you can go through that question also. So next we can discuss about the loss of refraction using Huygens principle. Loss of refraction as well as reflection. We'll discuss by using Huygens principle from wave optics chapter. We can go to the next question now. Okay. Using Huygens wave theory, using Huygens wave theory of light, show that the angle of incidence is equal to angle of reflection is equal to angle of reflection in case of reflection of a plane wave by a plane surface. Okay, this is actually how to prove loss of reflection using wavefronts. Plane wavefront, we are going to prove this one. Loss of reflection. Later we discuss about loss of refraction also. Okay, by using Huygens wave theory. Okay. So first I'll take one plane surface here. It may be mirror or reflecting surface. We'll take one plane surface. It may be on reflecting surface. Okay. Now on plane wavefront is going to incident here. This one plane wavefront incidents here. Okay. Draw one perpendicular line here to here. So this is the incident, is a direction, draw the like this. Now at the point of incident, we'll draw one normal here. This is a normal we'll draw. So this is angle of incident I. Okay. This point we call it as A and here is B. So what is that AB? AB is the incident to wavefront. Incident to wavefront. Whereas this and A strikes here and that undergoes reflection. And B will continue in the same medium, same direction that is going to continue. B is going to continue in the same direction. Okay. So AB is the incident wavefront. Now we have to calculate or find the reflected wavefront we should find. Okay. Now what happens is B and will continue in the same direction and is going to strike here. Okay. So what happens this A? A portion will get reflected this way. Okay. Now what we'll do is we'll measure the distance. At this point also we'll draw one normal. We'll measure distance from B to where? B to C. We'll measure distance from B to C. Okay. Now here what happens? This wave gets reflected from here in this way. Okay, we'll draw one normal to this one. What we'll do is measure distance from B to C. Same distance we'll measure it here and mark the point here, something like this. Okay. So we'll draw one line here to here. Now this angle we call it as how much here? R. It's the angle of reflection. At the same time, this angle also becomes how much here? R itself. Now this point I call it as D. So CD is known as reflected wavefront. And here is AD. So AB is the incident wavefront and CD is the reflected wavefront. And this angle also becomes how much here? I itself. This angle also I. This angle also I. And V is the speed of light in a given medium. So distance traveled from B to C and distance traveled from A to D both are same. Okay. So we'll take now two triangles here before that are right here. A BC value equal to which one here? BC value equal to V into D. At the same time AD equal to V into T. Now triangle ABC. Triangle ABC equal to how much? Sin I. ABC. I belongs to that one. ABC equal sin I equal opposite side. What is that? BC divided by what here? AC. Now what is the value of BC? BC is V into T by AC. I is your opposite side BC divided by AC. Next triangle ADC. R is here. So sin R is equal to opposite side. What is that? AD divided by AC. So AD value how much here? AD value is also same. V into T divided by AC. Equation 1 and equation number 2 equate both. Equation 1, what is that one? Vt by AC equal to Vt by, I'm sorry, these both are equal, right? Therefore, what we can write here is 1 and 2 equal left hand sides. Sin I is equal to sin R. Left hand side equal sin I equal to sin R. So sin will get both sides same. That becomes what? I is equal to R. I is equal to R. This is the law of reflection. This is the law of reflection. So what is the law of reflection says? Angle of incident is equal to angle of reflection. So AB is the incident wavefront and CD is the reflected wavefront. I is the angle of incident and R is the angle of reflection. So sine I is opposite side BC by AC. AC is the hypotenuse. So BC value how much here? V into T. AC value as it is. Sine R is opposite side divided by AD divided by the hypotenuse. What is that? AC. AD is equal to V into T. Now equate both sine I and sine R because right hand sides are same. So sine will get both sides sine I equal to sine R. That means what? I is equal to R here. Now this is a law of reflection. So what is the law of reflection says? Angle of incident equal to angle of reflection. So that only proved here by using Huygens principle and by taking plane wavefronts. Okay, we'll go to the next one now. We'll discuss the next one now. That is using Huygens wave theory of light derive Snell's law of refraction. Using Huygens wave theory. Huygens wave theory of light derive Snell's law of refraction. Using Huygens wave theory, we should derive Snell's law of refraction. Okay, we take now two mediums. One is rarer medium, other one is the denser medium. Okay. So here is a medium 1 and here is a medium 2. 1 and this is a medium 2. So refractive index in this medium how much here? We'll write as N1 and here is N2. So first we'll take one plane wavefront here, goes and strikes here. We'll take one plane wavefront. This is one plane wavefront, goes and strikes here. Okay. This point I call it as A and this I call it as B. Refractive index in this medium is how much here? N1. Okay, rarer medium and here is which one here? N2, denser medium. Now this end what happens? Undergoes refraction. Now this is traveling from A end. Before that we'll mark some angles. This angle we call it as angle of incident I. This angle also becomes how much here? I. Okay. Now what happens is A and that undergoes refraction traveling from rarer to denser will bend towards the normal. It will go like this. Now what about this end? This end goes where? Continue the same medium and strikes here. This and which one here? A, B. This I call it as which one here? C. Now this is traveling from where to where? Rarer medium to the denser medium. Once again this will bend towards the normal. It will go like this. Okay. Now what is this length? Speed of the light in this medium is how much here? V1 and speed of light in denser medium how much V2. So this length becomes how much here? V1 into T. Okay. Now we'll join the length from here B to C, that is V1T. Now at the same time we'll measure here also. Velocity in this medium is how much here? V2. Time taken by the wave to move from B to C, that is how much? T. Same time will take here also. It is going to travel less distance because it's a denser medium. Somewhere like this. So I'll draw one line here to here. Okay. Now this point I call it as now D. Now this CD is known as what? CD is known as refracted wavefront. CD is known as refracted wavefront, and this angle here is R. If this angle is R, here also becomes R itself. This angle becomes R. So all the namings we are done there. So just we start our derivation now. We have to prove the Snell's law. What is Snell's law says? The ratio of sine of angle of incident to the sine of angle of refraction is a constant, and that constant is known as refractive index of the medium. Okay, so I'll take the first triangle here, ABC. We'll take the triangle ABC. Which angle belongs to that one? I. So I'll write here sine I is equal to what? Opposite side, what is that? BC, divided by the adjacent side, what is, sorry, hypotenuse, what is that? AC. So BC value how much here? V1 into T, and AC value as it is. Equation number 1. Next triangle will take triangle ADC. Sine R is equal to opposite side. What is that? AD. Divided by the hypotenuse, what is that? AC. AD value how much here? V2 into T. AC value as it is. This is equation number 2. A to D value how much here? V2 into T. This value how much? V2 into T. V1 is the speed of light in the air, and V2 is the speed of light in that medium too. Rarer medium and denser medium. Next, what you have to do? We'll divide both the equations 1 by 2. Sin I by sin R equal to V1T by AC divided by V2T by AC. Now what happens here? AC cancels, T cancels. Sin I by sin R equal how much? V1 by V2. Equation number 3. Sin I by sin R equal to V1 by V2. Equation number 3. Okay. Now Snell's law says sin I by sin R equal to N2 by N1. So now we should bring the refractive index formula. So medium 1, refractive index how much here? N1, and the formula is C by V. So we can write here N1 is equal to C by V1. N1 equal to C by V1. Similarly, medium 2. N2 equal we can write as C by V2. If we divide this both, N2 by N1, C by V2 divided by C by V1. So CC will get cancelled out. That becomes here N2 by N1 is equal to V1 by V2. V1 by V2. Equation number 4. So sin I by sin R equal to V1 by V2. So V1 by V2 is N2 by N1. If I combine both, so 1 is equal to 2. So what we can write here? Sin I by sin R is equal to what here? N2 by N1. So just rearrange it. N1 sin I is equal to N2 sin R. The equation. This is the Snell's law of refraction. This is the Snell's law of refraction. Snell's law of refraction. Okay, we'll go through once again this derivation properly. Using Huygens wave theory of light, derive Snell's law of refraction. We have derived Snell's law of refraction. So I have taken one plane wavefront AB. This is the AB. This line and this line should be perpendicular here. This one should be perpendicular. Should be perpendicular here. AB is the incident wavefront. So this AN undergoes refraction. So B will travel as it is. When B goes and strike here C, so A is going to travel here. So distance traveled from B to C is V1t. So what we'll do here, we'll draw. At the same time, we'll measure the distance in this medium because in second medium speed is less, time will be same. So distance traveled will be V2 into T. So measure distance, draw one line here to here. So here becomes now, this angle is R, this angle also becomes R. This angle is I, here becomes I. And this angle is R here. First we'll take this triangle ABC. Sin I is equal to opposite side. What is that here? V1t by AC. BC by AC, that becomes V1t by AC. Sin R is opposite side AD by AC. AD is V2 into T by AC. Equation 1 by 2. So sin I by sin R equal to V1t by AC by V2 by AC. AC cancels, T cancels, so becomes sin I by sin R equal to V1 by V2, equation number 3. So in medium 1, N1 equal to C by V1 and medium 2, N2 equal to C by V2. Just divide both. N1 by N2 is equal to C by V1 by C by V2. C cancels, V2 by V1. Sorry, we written here N2 by N1 becomes a V1 by V2. So V1 by V2 equal what here? Sin I by sin R. So sin I by sin R equal N2 by N1. That is N1 sin I equal to N2 sin R. Cross multiply. Refractive index of the medium into sine of the angle in that medium remains constant. N1 sin I equal to N2 sin R. This is the Snell's law of refraction or loss of refraction. Okay. Okay, now we'll solve some numericals based on this way optics chapter itself, based on fringe width or Young's double slit experiment. We can try one or two questions based on this one. Okay. So take the question now. So one or two questions we'll solve here. In Young's double slit experiment, Young's double slit experiment, in Young's double slit experiment, wavelength of light used is 5000 angstrom and distance between the slits is 2 mm, that is 2 millimeter. Distance of screen from the slits is 1 meter. Find fringe width and also calculate the distance of seventh dark fringe from central bright fringe, from central bright fringe. Okay. In Young's double slit experiment, Wavelength of light used is 5000 angstrom. Distance of the slits is 2 millimeter. Distance of screen from the slits is 1 meter. Find the fringe width and also calculate the distance of seventh dark fringe from the central bright fringe. Seventh dark fringe from the central bright fringe. Okay. First we'll write given data. What are things are given here? Wavelength is given 5000 angstrom. So lambda value 5000 angstrom. That means 5000 into 10 to the power minus 10 meter. Angstrom means minus 10. Okay. Then distance of the slits small letter d, that is 2 millimeter. That is 2 10 to the power minus 3 meter. Distance of screen from the slits capital letter d is how much here? 1 meter. Find the fringe width and also calculate. Fringe width you have to calculate. Fringe width beta you have to calculate. Also calculate distance of seventh dark fringe. Okay. Dark fringe. Dark fringe distance. Distance of seventh dark fringe. X7 is to calculate. Okay. First we'll calculate fringe width. Fringe width formula is what? Beta equal to lambda capital D by small letter d. Beta equal lambda into capital letter D by small letter d. Okay, we'll calculate this now. So beta equal to lambda value, wavelength value, how much given? 5000. So 5000 into 10 to the power minus 10 into d value how much? 1 meter divided by small letter d. 2 10 to the power minus 3 meter. Just solve this one. 5 by 2 becomes how much? 2.5 into 10 to the power minus 4. So here 3 zeros are there and here minus 3 goes up, becomes how much? Plus 3. So 3 plus 3 becomes 6 and minus 10 is becomes minus 4. So 2.45 into the power minus 4 meter. That is a fringe width. Direct substitution you do. This is a fringe width. Okay. Next one. Distance of nth dark fringe. Dark band or dark fringe. That formula is xn equal to 2n plus 1 lambda d divided by 2d. 2n plus 1 2n plus 1 lambda d by 2d. Okay. So the formula now. So xn is equal to 2 into n. N value how much here? Since I use the formula here 2n plus 1. So n value becomes here how much? 1 less, that will take 6. Because 2n plus 1 you are taken. When you take 2n plus 1, that means our first odd number is 1. To get to 1, n value should be how much here? 0. Like that you have to count. Seventh one becomes here 6. N value becomes 6. So 2 into 6 plus 1 into lambda 5000 into minus 10. Capital D is how much? 1. So 2 into small letter d is how much here? 2 millimeter. So xn value how much here? Xn value equal to 2 into 6 becomes how much? 12. 12 plus 1, 13. 13 into 5000. 13 into 5000 you can multiply that, becomes 65,000. Divided by how much? 4 is there. Then those minus 3 goes up, become plus 3. Already 16.25 is there. That becomes 16.25. 16.25. 6.25 in 10 to the power minus 4. Or you can shift the decimal point this side and we can write as 1.625 10 to the power minus 4 meter. So position of the nth dark band is 16.25 10 to the power minus 4 meter is answer. 16.25 10 to the power minus 4 meter is the answer. So Young's double slit experiment, wavelength of light used is 5000 angstrom and distance from the slits is 2 millimeter. Distance of screen from the slits is 1 meter. Find the fringe width and also calculate the distance of seventh dark fringe from the central bright fringe. So lambda value written here 5000 angstrom. Small letter d is 2 millimeter, 2 to the minus 3 meter. Capital D is 1 meter. Fringe width you have to calculate. Dark fringe x7 you have to calculate. N value is 6. So fringe width beta equal lambda d by small letter d. Lambda is 5000 angstrom into capital D is 1 and small letter d is 2 millimeter. And distance of nth dark band of dark fringe 2n plus 1 lambda d by 2d. Just your substitution. Answer becomes here 16.25 10 above minus 4 meter is answer. Now if you want you can do this like this also. 2n minus 1 lambda d by 2d also you can write. But in the place of n you should write it as how much is 7 only. Okay. If you do that also answer comes same here. If you want you can try that one. Instead of this one you can go with this formula. I'll do it here. Xn is equal to 2n minus 1 lambda d by 2d. This is a formula. But n value you write how much? 8 only. Sorry, 7. 7th fringe is given. So 7. 2n that is 2 minus 7. 2 into 7 minus 1 into lambda. Lambda value how much here? 5000. Into capital D is 1. Into 2 into smaller d is how much? 2 millimeter. 14 minus 1 become a 13. 13 into 5000 same 65,000 divided by 4. So you are going to end up with once again same answer itself. But you should know this concept. If you use 2n minus 1, that formula pattern if you use, what are the fringes given? Dark fringe, same number you have to select. If you use a 2n plus 1, then you have to go with the 1 less. Actually because n start with a 0, that's 1 less. N start with the same number 0. I'm sorry, now start with the 1. So same number you are going to get. Okay. So next concept here. Next concept we can discuss here. So you already we discussed about Brewster's law in the previous class. Already we discussed that one. There comes on Malus law. Malus law. What is the Malus law says? Malus law formula. I is equal to I naught to cos square theta is the formula. I is equal to I naught to cos square theta. So just to write that Malus law or Malus equation. For the formula, I is equal to I naught to cos square theta. I is the intensity of the polarized light. I naught is the this intense analyzer. I naught is the intense the first polaroid. Cos theta. Theta is the angle between analyzer and polarizer. I is equal to I naught when theta is equal to how much? 0. And I is equal to 0 when theta is equal to 90 degree. When theta is equal to 90 degree, I becomes how much? 0. And only transverse waves can be polarized. Only transverse waves can be polarized. Longitudinal waves, that is sound waves, cannot be polarized. Light waves are transverse waves, therefore they can be polarized. Okay, next one we can discuss about uses of polarides. Next point we can write here, uses of polarides. Next we can write here, uses of polarides. Okay, Okay, first one, to control the intensity of light in sunglasses, window pans, etc. Second one, in photographic cameras, in photographic cameras and 3D movie cameras, in 3D movie cameras, to improve the color contrast, to improve the color contrast in old paintings, to improve the color contrast in old paintings. So first one, to control the intense light in sunglasses, window pans, etc. Second one, in photographic cameras and 3D movie cameras. Third one, to improve the color contrast in old paintings. To improve the color contrast in old paintings. So these are the uses of Polaroids. Using sunglasses, window pans, etc. Photographic cameras and 3D movie cameras to improve the color contrast in old paintings. In places Polaroids are used. Okay, what is Polaroid? Polaroids are the devices used to produce plain polarized light. Polaroids are the device used to produce plain polarized light. Okay, so I hope this much is clear here. I'll stop here now. Other things we can discuss in our next class. Okay, thank you.